I would like to welcome Jose Garcia, assistant professor at Sac State. He is their resident concrete expert and is going to share with us as much as he knows. He says he can talk all day about concrete. We only have about half an hour, but I'm looking forward to it and hopefully building some more discussions around concrete, because I'm going to invite Professor Garcia to share his screen and begin his talk.
All right. Well, thanks for that wonderful introduction, and good morning to everybody. I'm really glad to be here. Thank you for having me, and I hope you enjoy my presentation. So with that, we'll go ahead and get started. So my name is Jose Garcia. I am a professor in the Department of Civil Engineering at Sac State, and I figured we'd get started by just letting you know a little bit more about me. So all three of my degrees I got from the University of Texas at Austin, and it's I lived in Texas the vast majority of my life, so it was a bit of a culture shock coming from Texas to California. But I'm really glad that I made that move about 3 years ago. And it's been fantastic. I fell in love with California, so I'm really glad to be here. But just to give you a little bit more information about me, so I got my bachelor's and my master's of science in civil engineering. After that, I went to the industry. I worked as a structural engineer for a couple years full time before deciding to go back to school, get a PhD, so that I could teach. And I kept working as a structural engineer part-time to kind of help pay for school and stuff. So that's where I worked. It was a small firm in the Dallas area. And then after that, when I focused on my PhD and started doing research, I graduated back in 2018. About 3 days after I defended my dissertation, I was on the road out west to come to California, and I've been here ever since. Now, when people ask me what I do and I tell them I'm a professor of engineering, they think that I work on really cool stuff like robots or spaceships or things like that. And then I do work on very cool stuff, but I tell people that I actually study concrete, and I get this very weird look on their face. I get one of two responses. They tell me, you study what? There's actually people that study concrete. Or I get a response of, what's concrete? Are you talking about cement? And then the engineer in me really has to bite his tongue to not respond in a mean way, because that's one of my biggest pet peeves. But the picture that I'm showing right now is my favorite building in the entire world. If you've been in Rome, you might recognize it, but this is the Pantheon in Rome. That was built about 2,000 years ago. It was built as a place of worship for all of the Roman gods, and then it kind of got taken over by the Catholic Church. It's still used today as a Catholic temple, but this shows the beauty and the durability of concrete. If done correctly, it can last thousands of years. Now, the Romans were experts at this stuff, but this just shows you what a durable and wonderful material this can be. All right, so going back to one of my biggest pet peeves, cement and concrete are often used interchangeably, and they're different things. So just to make sure that we're all on the same page, I would like to speak a little bit about concrete and cement and give you a little bit of background information, because that's going to be relevant for the presentation today. All right, so cement is actually not equal to concrete. Okay, cement is the gray powder. Concrete is the solid stuff, and cement is an ingredient that's required to make concrete. Okay, so the analogy that a lot of people like to use is the analogy of a cake. Okay, so cement is to concrete as flour is to cake. And this works out great because if you look up, for example, fruitcake, you can see, hey, that looks very, very similar to concrete, where we have the cement and the water combined to form a paste. That's what holds the cake together. The rest of it is aggregate, basically sand and rocks. That's the vast majority of the concrete that's held together by that binder, by that paste. Okay. If we were to look at it in a little bit more detail, this is what's required to make concrete. I have to have some cement, the gray powder. I have to have some water. Here's my rock and here's my sand. I get all 4 ingredients. I throw them into a mixer, mix for a few minutes, and then I get this material that's going to start out as a liquid. It's going to flow and it's going to take any shape that I want. And after a few hours, it's going to turn into a solid. If you look at, and you can get very creative with it, but this is just your basic plain concrete. And if you look at the ingredients in terms of the proportions by volume, typical concrete is going to look something like this. You're going to have some air in there. Sometimes that's intended, sometimes it's unintended, but that's going to be there due to the mixing action. When you're mixing the concrete, some of the air is going to get trapped in there and it's going to remain there. Maybe not as much as 8%. Sometimes it's going to be around 1 or 2%, but it is going to be there. Okay, so concrete requires 7 to 15% cement. You can see the vast majority of it is going to be my sand and my rocks, and I'm going to require a little bit of water. Okay, so this is basic plain concrete. Okay, some quick facts about concrete. It's the most widely used material in the world. It's the second most widely used substance in the world. The only thing that we use more than concrete is water, which is amazing if you think about it. In the US, more than 70% of bridges are made out of concrete. The tallest building in the world, the Burj Khalifa, which is located in Dubai, and it's a beautiful building. I forget the exact number of stories. It's made out of high strength concrete, dams, infrastructure. And basically everything around us is made out of concrete. This slide shows all the different applications which we really don't notice, or at least the average person doesn't notice. I'm fascinated by this stuff, so I like to go and look at everything concrete related. But the roads that we drive on, the bridges that we drive over, are sewage system. Okay, so drainage pipes, sewage pipes, drinking water pipes made out of concrete, dams, water treatment plants, foundations, in addition to buildings. Okay, so concrete is everywhere. So the question is, how do we produce concrete? Well, the very first thing we have to do is we have to produce cement, because cement is the key ingredient when making concrete. We need cement. That's what's going to provide us with the strength. That's what's going to give us the binding ability to hold everything together. Okay, so how do I produce cement? Well, I've got to take some limestone, which looks like this. Limestone has a chemical composition of calcium carbonate. I've got to throw that limestone in a big giant oven at a very high temperature to trigger a chemical reaction that we call calcination. We're basically going to take that calcium carbonate, we're going to split it into calcium oxide, which is known as lime, and we're going to separate carbon dioxide away from the limestone. That carbon dioxide is going to be in the form of a gas, and it's going to be released into the atmosphere. Okay, so I've got two different things going on here. The calcination reaction is releasing CO2 gas, and also I have to reach a very high temperature in the oven that's going to require fossil fuel burning, which is also going to release CO2 into the atmosphere. Okay, so I get all of this so that I do all of this so that I can get lime, and then I get the lime, I combine it with other ingredients like sand and alumina or iron or basically other ingredients to get cement. These are all combined in the same oven. And the final product, without getting into the nitty-gritty details, is going to be the cement. Okay, so if some people have done an in-depth analysis, the National Ready Mixed Concrete Association has a fact sheet that has estimated that for every kilogram of cement that's produced, there's 1 kilogram of CO2 that's produced. Okay. About 60% of that is going to come from the chemical reaction, and 40% of that is going to come from burning fossil fuels that allows us to reach that high temperature. Okay, so it's a significant amount of CO2 that's emitted. The cement production is an energy intensive process. Recently, I would say maybe 10 to 15 years or so, the cement and concrete industry has caught a lot of heat from environmental groups, and rightly so, because there's a lot of resources that go into making cement. There's a lot of CO2 emissions, like I just showed you, and there's a lot of things going on. Okay? What people don't tell you is that concrete is actually a very environmentally friendly material. And don't get me wrong, okay, I'm in addition to being an engineer, I'm also very passionate about the environment. I think we can, and I think we should do better. Okay? But I'm here to tell you it is possible. It is possible. So just as a reference, I would like to show you other materials that we make every single day. Okay, so this figure, here's the reference for it. This figure shows the embodied carbon for different building materials. Okay, and this embodied carbon, this is from production all the way until the material makes it to the job site and it's in place. Okay, if you look at cement, it falls down here. Okay, so I've got 1 kilogram of carbon dioxide per kilogram of building material. Cement falls up here. Now, because cement is required to produce concrete and we only use, let's say, about 10% of it, when we actually produce concrete, concrete ends up down here. Okay, because the rest of the stuff, the rest of the ingredients, water and the aggregate are local. There's not a lot of transportation that's required. So it ends up being a very environmentally friendly material, especially when you compare it to others, like the metals. You might notice a lot of metals are up here, like aluminum and steel. Steel's all the way up here at 2.7, even when you compare it to a material like timber, which a lot of people are saying it's a material of the future. You may have heard about cross-laminated timber. It's very popular up in the Northwest. I think Portland and Seattle are making a big push to start building more out of timber. And I think that's great. I think that is one solution to help reduce CO2 emissions. But we shouldn't be so quick to discount concrete because it is a very, very viable material and it's getting even better. The other thing that people don't tell you about concrete is, yes, it's energy intensive, but also we take a lot of waste materials and we put them into concrete. These materials would otherwise end up in a landfill. Nobody has use for them. We throw them into concrete instead of it having to go into a landfill, and it actually makes concrete better. It makes it stronger. It makes it more durable. It makes it less expensive. So everybody wins. You may have heard about some of these materials, especially fly ash. Fly ash is a very popular one. Fly ash is a waste byproduct of the coal burning industry. So whenever we burn coal, there's some ash that falls to the bottom and it's collected, and it looks like this. And again, nobody has a use for it. Some people figured out, hey, we can throw this into concrete. It's going to drive the cost down. It's going to make it better. So it's added every single day. This is used every single day. Other waste materials that are thrown into concrete. Slag cement, which is a waste byproduct of the steel manufacturing industry. That's the picture in the middle that you see there. That's a steel foundry. The white stuff that you see, the white powder next to it, that's what slag cement looks like after it's processed a little bit. And this stuff is absolutely wonderful. It makes concrete very, very durable. In Europe, they really like to use it because it makes concrete almost impermeable. So it's great for marine applications. The last picture that you see here, the high-tech one at the bottom left, this is a ferrosilicon processing, basically silicone chips. Again, we have some waste products, silica fume. That's the dark blue powder that is very, very tiny. It's so tiny that it goes and finds space inside of concrete to fill. And again, it makes it stronger, it makes it more durable. Okay, so that's one way that concrete is helping out the environment, by absorbing all of these materials and basically not allowing them to get into a landfill. All right, so how can we make it even better? How can we produce concrete that is even more environmentally friendly? Well, the cement production is the process that requires the most energy. So anything that we can do to reduce the cement that's going into the concrete is going to be helpful in that regard. Because SCM, supplementary cementitious materials like fly ash and slag and silica fume, those replace a portion of cement. The more SCMs, the more SCMs that we use, the less cement that we use. So less CO2 overall, less CO2 emissions, more environmentally friendly. There are different types of cement that we can use. One hybrid is a Portland limestone cement, which I did a lot of work on during my PhD, and that's something that we're going to talk about here in more detail in just a second. There's researchers that are looking into alternative cements that are more environmentally friendly, but maybe a little bit more dangerous to use, so you have to be careful with them. These are more specialty applications. There's nothing that we can do to replace concrete. We use so much of it. It's not going away. We have to make it better, and we can make it better, but we're not replacing it. We can't build out of steel. I already showed you it's going to be less environmentally friendly. And then timber, it's about the same as concrete, but how much do we have before we start running out? There are some people that have started looking into very interesting ideas. There are some researchers at UCLA led by Professor Gaurav Sant. They recently obtained I believe it's a $7.5 million grant that is looking into injecting carbon dioxide that you're collecting from the cement manufacturing process or from other industrial processes. You're taking that carbon dioxide and you're injecting fresh concrete with it. And that's another way to make the concrete better and stronger, and you allow it to cure faster. The technology is not quite there yet, and that's why there's a lot of research funding that's being redirected into some of these cool ideas. But building codes move in a geologic timescale. It's going to take years, if not decades, before we start, before we have enough data that shows this is safe, that shows we can start using it in a widespread, on a widespread scale. So we've still got to do other things while the new technology is adapted. The other thing that helps from an environmentally friendly perspective is making the concrete more durable. If we can make concrete last 50, 100, 200 years, that's concrete that doesn't have to be replaced. That's natural resources that we can save for something else. It doesn't matter if we have the greenest concrete in the world. If we have to replace it after 1 year or 2 years because it's deteriorated, then that's not really environmentally friendly. So what can we do to make it durable, and what can we do to also try to help out with CO2 emissions as much as possible? And that's kind of what I do for a living. That's what my research focuses on. And there's a lot of other, there's a lot of research that's going into this. We could talk about this for days, what other people are doing. Thomas, you sent me an article that was looking at the incorporation of graphene, which is a very, very strong material, into concrete. And again, that's another interesting idea, and I think it's one that has a lot of merit. Right now, the technology is not there. So I think having research funding go into it and verify it and giving concrete practitioners enough time to adapt and make sure that this is a viable solution is going to go a long way, and we should definitely be investing in it so that we can take advantage of that in the future. But I'm more of a what can we do now type of person. Okay, so that's what I'm focusing on. Okay, so what can we do now? Portland limestone cements have been getting a lot of popularity. Portland limestone cements have been around they're relatively new in the United States, but they've been around for a long time. In Europe, they've been doing research on Portland limestone cement since the 70s. They've gained more popularity in the US, and finally back, I believe about 10, 15 years ago, the standards finally allowed the use of limestone in cement. And this is actually what I worked on for my PhD at the University of Texas at Austin. The Portland limestone cement basically takes some ordinary cement and combines it with limestone that is pulverized. Okay? It is ground into a very fine powder, and it is combined with the cement, usually in relatively small proportions of 5 to 15%. But my research was looking at increasing the limestone portion to as high as about 30%. Okay? And why would we do that? If we already have cement, why would we combine it with limestone? Well, the Europeans figured out that if you take about 15% limestone, up to about 15% limestone, you grind it up, you're diluting the cement, which is what's requiring the natural resources and the CO2 emissions. But you dilute it with this raw limestone, and it's going to not affect the properties, the engineering properties. It's not going to significantly affect the strength. It's not significantly going to affect durability. But that 5 to 15% replacement of cement is going to reduce CO2 emissions by about the same amount. It's going to essentially mean we can now use less cement to get the same product that we were getting before. Okay, so the question is, well, can we push that? Can we push the envelope more? Instead of limiting to ourselves to 15%, Can we go to 20%? Can we go to 25%? And then in addition to that, what my project focused on was the addition of supplementary cementitious materials, the stuff that would otherwise end up in a landfill. Can we also throw some of that in there because it was already making concrete better and stronger before? So can that work in conjunction with the limestone to make a good, high quality product and reduce the cement content? And the answer that we got was yes, we can still get a very good product using 50% the 50% of the cement that we were using before. Okay, so some of the advantages and disadvantages of the Portland limestone cement, it's very similar to ordinary cement. You don't need special equipment. You don't need to train the contractor in a different way. You don't need to do anything special because this all happens at the plant. The limestone is added. It's going to change a little bit. So somebody that's been doing this a long time, they're going to recognize, hey, the cement's a little bit different. It's going to be a little bit wider because of the higher limestone content. But other than that, it's going to essentially be the same product. Okay, so this is what I was talking about. Our project showed up to 50%. Yes, it's going to decrease the strength a little bit because we have less cement, which is what's providing the strength, but not so significantly that we can't use it anymore. We can still use this concrete, especially in places where we don't require the concrete to be that strong. For example, sidewalks, pavements, slabs for buildings. We don't require concrete that is super strong like we would do, for example, in a column of a building. Okay, so we can kind of mix and match and really put the pieces of the puzzle together to get to use this quality product in the places where it's going to result in lower CO2 emissions. It's going to result in a more environmentally friendly product. Okay, so that was back in 2018. It does have some disadvantages. Like as I mentioned, we're diluting the cement, so the compressive strength is going to take a hit, and perhaps the biggest obstacle to that is the impact on the construction schedule, because concrete gains strength over time. When we're diluting the cement content, it's going to gain strength a little bit more slowly. And unfortunately, we live in a microwave kind of world where we need an answer now. The contractor can't afford to wait an extra week for the concrete to gain sufficient strength. And that's something that's going to have to change over time if we want to take advantage of not only this product, but similar products. There's going to have to be something that gives. And I don't really have any bright ideas on how to accomplish this other than maybe incentivizing the contractor to kind of get the concrete down, give it enough time, maybe go to another project and then come back. So, but that's a story for another day. So like I said, that was back in 2018. That's what I did for my PhD. And then when I got to Sac State, there wasn't really anybody in the department that does what I do. We've got a couple of very brilliant structural engineers, and I don't really focus on structural engineering. I focus more on the material science side of things. I study concrete in detail as a material, and I try to make it as durable as possible. I try to make it as environmentally friendly as possible. So basically, when I got to Sac State, I wanted to set up a lab that would allow us to study this. So I'm very interested in concrete durability. Okay, that's my main area of expertise, but I also want to get into other things like structural rehabilitation and repair. Instead of tearing things down and replacing them, it's much faster, less expensive, and more environmentally friendly to repair it if at all possible. Looking at novel materials that's going to help out the environment. Ultra high performance concrete. Thomas, this goes back to the article that you sent me. Because graphene is a very strong material, it's going to make the concrete super strong. If the concrete is super strong, we can get away with smaller elements, smaller columns, smaller beams, which is going to require less concrete. And again, less cement. So more environmentally friendly and sustainable infrastructure. And the approach that I'm taking now for my research is a combination of these things. I've got some graduate students that are interested in what I do, and we're going into the lab. And unfortunately, with the pandemic, we had to slow down a little bit. But now that we're seeing the light at the end of the tunnel, we're ready to get back into the lab and hit the ground running. The other very nice thing about having ended up in California is that there is a lot of, at least fortunately for me, there's a lot of durability issues. Where we live in California, there's a lot of alkali silica reaction, which attacks concrete from the inside. There's a lot of sulfate attack because our groundwater, our soils have a lot of sulfates. When they penetrate concrete, they start attacking it. They start kind of eating it away. And I have some pictures here on the next slide, but these are very, very common in California. Okay, so picture on the left shows you what alkali silica reaction looks like. This is very, very typical. And then you can see the picture on the right with where the concrete is right up against the water. It looks like somebody's been eating away at the concrete, and that's essentially what's happening with the sulfates penetrating. Corrosion is the #1 headache for concrete in the entire world. Ironically enough, this is not a problem in the concrete. This is a problem in the steel that's required to reinforce the concrete. The steel doesn't want to be steel. It wants to be iron oxide. So eventually it turns back into iron oxide over time. Concrete does help it in that it's a lot harder for the steel to corrode, but it is going to happen. And it can get severe enough to look like that. It's very aggressive in coastal regions. It's also very aggressive in colder climates, like in the Sierra Nevada region. There are other things that attack concrete. Freeze-thaw damage, again, this is in the Sierra Nevada region, where we have a lot of cycles of freezing and thawing. Basically, you have water inside of concrete penetrating it, temperature drops down, the water freezes, and it causes the concrete to start exploding from inside. Very similar to what would happen if you got a Coke bottle and you stuck it in the freezer and you left it overnight. That Coke bottle is going to explode as the Coke freezes. So there's a lot of different things that we have to be careful of, especially as we're looking at these new materials. We have to make sure, are they still giving us a durable product? Okay, this goes back to, it doesn't matter if we're using 10% cement. If it's going to last us 6 months, it's of no use to us. We have to make sure it's still a durable material. Okay, so these are some pictures of the picture on the left shows the freeze-thaw damage. That's what happens when the water freezes inside of concrete. And then, excuse me, whoops. And the picture on the right shows concrete carbonation, which is a significant concern when you start driving the cement content down. It's easier for the concrete to carbonate. It lowers the pH. And when the pH is lowered, it makes the steel more prone to corrosion. It's not as well protected. So what I'm doing, what I want to do is basically simulate the type of lab that I was working at when I was a student at UT Austin, basically get the new materials, cast concrete samples, put them out, and expose them to the elements and see what happens. Basically, invest the time, invest the effort to see, are these materials viable? This is a picture of, well,
let me just ask. I mean, we're sort of pushing on time here, but obviously we're all concerned about the building collapse in Miami, and I see now there's several mechanisms that could have contributed to that, and I'm sure you've looked at it. Do you have any comments on what happened there?
You know, I have kept up with it. I would, you know, I don't want to get into specifics because I don't know the full story, and it would be inappropriate for me to comment on, you know, I think this is what happened. But I think probably a combination of things. There was the California Structure Safety Commission or something like that commented on CNN that mentioned corrosion was probably one of the factors that came into play because of the fact that the condo collapsed in the on the seaside, where corrosion is known to be more aggressive. All the chlorides are getting in there and attacking the steel. So I think that had to do something with it, but they're still looking into it. But I believe some of it was due to design. Some people have said that the drainage wasn't working properly, and that's also going to cause the concrete to get into trouble. Corrosion was an issue. There's a bunch of structural engineering reports that came out that said, you know, back in 2018, they identified some issues that I don't believe were addressed at the time. So a combination of things, but definitely something like this, I believe, could have helped if they would have tested the concrete to see how long is it going to last, especially in an aggressive region like Miami, where it's right up against the ocean.
And also, are you familiar with a local company here called Sierracrete?
I can't say that I am, no.
Well, they use wood waste. So it's just, it's ground up wood waste. And I think there's something about the fiber content that makes the material stronger, but they reduce some of the other components as you've described. And they're having some success. There are other companies that are actually pursuing some of these alternatives across the country and across the world, of course, but wood waste in cement, any comment on what that does? Does that improve the strength?
I'm not too familiar with that, so I would have to look into it. I wouldn't be able to comment on that. There's a lot of things that you can use. There's a lot of materials that you can incorporate. Some researchers at the University of California at Berkeley have looked at things like rice husk ash, especially in places like India and China, where they're producing a lot of rice. And you know, you have all of this waste, of all of this wasted husk, and it turns out that actually also helps out the concrete. One of my graduate students right now is looking at incorporating high density polyethylene, basically the plastic bottle caps that are ending up in landfills and they don't get recycled and stuff. Or if they go to a recycling center, they can get turned into pellets. We can pulverize them and incorporate it into concrete. So my graduate student is interested in that, and we're setting up some experiments now so that we can take a look at how the properties are affected.
So one quick thing I want to
know, but there are others on the call that might know. I mean, one of the questions is, with all these ways to reduce the CO2 emissions from concrete, are concrete manufacturers subject to having to use carbon offsets for all this CO2 emission? I couldn't get any confirmation on whether they are or they are not. But if if high CO2 content cement were more expensive, that might narrow some of the economic difference here. Do you know anything about whether they are required to purchase carbon offsets, or anybody on the call know?
That's a really good question. I do want to give Professor Garcia a chance to answer that, but I was hoping to ask him if you could quickly do the research center that you're trying to set up at Sac State. If you could tell us about that really quickly, and then we could jump into questions.
Sure. Yeah, I've got just a few more slides that show you that shows you the vision, and then we can jump to the questions after that. So I'll skip over this slide. Basically, this is telling you that we're trying to do long-term testing, because that's going to give us the best data instead of the typical lab testing that we do. And like I said, this is at the University of Texas at Austin, where my advisor started doing this 20 years ago, and these blocks are still being monitored today. Okay, so at Sac State, I'm trying to simulate something like that. This is what the center is going to look like. Right now, the bones are in place. Basically, I convinced the university to give me an outdoor space and an indoor space where I could have all of my equipment. I could have my grad students working in there, and it's in a really great location. You can see the Guy West Bridge in the background. I don't know if you've been to the Sac State campus, but that's like one of the landmarks at campus, and it's a very beautiful bridge. It's a replica of the Golden Gate Bridge. So the lab would be located just down the street from it. This is a plan view of it. So the indoor lab would be here. That's where all of the fancy equipment is going to be located. And then I'm hoping that you can see my pointer here, but the rest of the lab, okay, good. The rest of the specimens are going to be located throughout the lab. This is what it's going to look like. Like I said, eventually we're still working on it, but it's going to allow us to do all sorts of fancy tests. We're hoping to get undergraduate and graduate students involved. We're hoping to get industry partners involved. But the plan is to basically turn this into a center where we can conduct research, and we can attract a lot of all of this research from the Northern California area. And this is going to allow us to collaborate with people like the UCLA researchers. This is a picture showing what the inside of the lab is going to look like. And some of the labs already in place. This is going to be known as the Advanced Laboratory for Infrastructure Materials Research, or ALIMAR. And basically, this is going to allow us to, number one, prepare students for a career in the concrete industry in the future. But it's going to basically give us a means to invest and hopefully get a lot of very useful information that will pay off in the near future. Okay, so there's my contact information. I can talk about concrete all day. I know that we're already pressed for time, so if you would like to reach out to me, please feel free to do so. That's my email. That's my office phone number. Right now, with the pandemic, I'm not in the office very often, so by far the best way to reach me is by email. But eventually, and we can set up a phone call in the future if you'd like. But just reach out to me, and I'd be more than happy to answer questions and talk about anything else in more detail.
Excellent. Thank you for giving us that encapsulating 101. There's a whole bunch of stuff on concrete there, and cement, and ways that you can impact carbon or the emissions of it. One thing I have a question for you on those. So you laid out this testing center for the structural and like how, the quality of kind of cement. Is there anything looking at testing the emissions or ability for cement or concrete to absorb carbon in the kind of in the center? And what funding are you looking at to support the center?
That's a fantastic question. Concrete is actually a material that absorbs CO2 naturally, and this is actually what that test measures. When concrete is exposed to the environment, it's going to, the CO2 is going to penetrate, it's going to change the chemical composition, it's going to be chemically bound. Typically, that's a bad thing, not for the concrete, but for the steel. Because when the CO2 penetrates, it carbonates the concrete, it lowers the pH, and at a lower pH, the steel starts corroding. But from a concrete perspective, carbonation is actually a good thing. It makes the concrete more volumetrically stable, it makes it stronger, and it makes it basically closes down the pore system inside that makes it very hard for deleterious chemicals to come in and penetrate it. So from a concrete perspective, that's a good thing. And like I said, this happens naturally over time. All concrete carbonates, depending on what's exactly in the mix. Some concrete's going to carbonate faster than other concretes. What the researchers at UCLA are doing is that they're injecting the CO2 into fresh concrete to force the concrete to become stronger immediately and to make it less permeable immediately. I'm not too familiar with that process. I know that you need some special technology, and at UCLA they have the resources to do something like that. We're more of a teaching institution with a little bit of research on the side, so we wouldn't be able to do something like that. But it is possible, and that's why I'm hoping to establish this so that we can start working with other universities like UCLA and like UC Davis, which is down the road. It's a fantastic research school where we can work together to find solutions for these problems. As far as funding, I recently got a grant from the American Public Works Association, where they kindly donated $25,000 to help us out with this effort, so that we can get fancy equipment and that we can get this center going. There are also some industry partners like Odin Construction that has a lot of interest in establishing this center. So they made a donation that's going to help out the outdoor lab. In addition to that, we're looking at other funding opportunities, both at the federal agencies and state agencies, and also industry partners.
We got a good, cool brainstorming thing from Akasha there, is have them build cool things like an amphitheater to test that you're testing the seats in, which is cool. One thing I wanted to ask about, so in California, the Air Resources Board typically is the one who goes in and enforces the air quality around concrete, people, where they're mixing it and putting all the cement together. And I know the CEC has expressed interest in focusing on carbon reduction through a lot of its programs. Now, since you guys kind of focus, I guess, more on education, not the research portion of it, is there a space where, like, the Air Resources Board and local communities can engage with Sac State about learning, how the concrete in their community, whether they're, mixing it in their backyard for a patio or something like that, impacts their air quality?
That's an excellent question. I'm not very familiar with the regulations. That's more of the environmental policy and that sort of thing, which is something that that's not my background. So I wouldn't really be able to answer that, unfortunately.
Well, I mean, this is a whole area that most people are not familiar with, and you've really done a great job of educating us all. And I don't know that it gets the attention it should. And I'll have to go back and research whether or not they're required to buy carbon offsets. They probably should be, so that we can stimulate more innovation. But big round of applause for Professor Garcia and the presentation this morning. Fascinating.
Thank you.
I mean, well, there's also been an interest in looking at not only green concrete, but green steel. Steel creates a lot of CO2 emissions too. And we'll try to get something together on that. But fascinating stuff, and so glad to have you in the community, Professor Garcia, and worrying about problems like this. So Thomas, I'll send it back to you to wrap it up. We've run a little over time here, but just remind people about our next episodes.
Yes, absolutely. I want to again thank Professor Garcia for joining us, and we're going to have to invite you back for a clean tech meetup where we focus on materials, because it's often overlooked. And in your slides there where it showed the emissions from steel, not to just mention concrete, and these are things that we don't have a whole lot of green substitutes for, besides greening the processes that we already have. So thank you very much for joining us today.